Good day. Welcome to the Electronics and Communication Systems course lectures. As we know that in the 5 units, the first unit is electronic circuits and op-amp, and second unit is communication systems and analog and both digital with a different multiple access, and unit 3 is transmission lines. We have seen quite reasonable problems on that, and waveguides. We have a different types, and we have seen briefly about concepts, and now we are going to see the scattering matrix parameters. This is also called ASE matrix, and after that we will be seeing the transmission matrix. It's nothing but ABCD matrix, and signal flow graph. This is basically used in the microwave circuit analysis, especially if it is it is similar like a small signal analysis in the analog circuits, where you have active circuits and different cascade systems. So signal flow graph is a technique used in the circuit analysis. And then we have impedance matching. In that we have a single and double stub tuning. It's nothing but both are different techniques of matching. It's quite important to match the impedance of the transmission line or microwave circuits. And after that it's a graphical techniques to solve the impedance matching problems by using a Smith chart. So this is very quite important tool, important topics for designing the circuits, microwave circuits, and analyze the circuits. So it is quite significant in the real time. So now we will go to the scattering matrix parameter. It's nothing but ASE matrix. So we will see these parameters. Like before that, we will see in broader what is the microwave network analysis techniques in general. So here ASE matrix and transmission matrix is a part of microwave network analysis. So what is a network analysis? Especially microwave is a high frequency network analysis. So this networks can be consist of devices. Especially it can be a pin diode. It is similar like a PN junction diode, which is but it's operate in a higher frequency, and we have a different components, microwave components, as like in the attenuators and different sources. For example, klystron source, that we will see it in another unit, and there are different filters, microwave filters, band pass, low pass, high pass, different filters and amplifiers, and etc. So if we couple together, it can be with the transmission lines, or if it is in a high frequency, so in a waveguide. So when we connect together, it becomes a network. So when we have a network, we should know the voltage and current of each point, each node of the network, to design that and to know what is my voltage and current in each point of the node. It is something quite similar to the electrical circuit analysis. So the same thing is applicable here. So we can effectively design the network and analyze it. So it's quite important also. So in the low frequency, we have a circuit theory techniques, for example KCL and KVL. So I'll try to make it a slideshow. So here what we do with basically with a microwave network, we effectively want to transfer the desired signal. It can be a filtered signal, it can be an amplified signal, or it can be just transmission of a signal. So the network plays an important role. So KCL and KVL is basically used in the lower frequency, that used to find out the different node voltage and current. So but in a higher frequency, can we use that same circuit theory? We will see that we can use that for some extent, but when we see as a practical reasons, we cannot fully rely on the circuit theory, so we need to some other theory, just some other way of doing approach the high frequency networks that we will see shortly. So at micro frequency, we don't totally neglect the circuit theory, KCL, KVL or different is that Y parameters, but we will use it for certain extents wherever we need it. It will be quite useful, so that we will use it and in a different way. So if you say that we will design that microwave circuits intuitively where it's necessary, as I mentioned, if I want the terminal voltage and current, can I achieve it using the circuit theory? Yeah, if I can achieve by using the if it is a signal is lower frequency. But if what happen if it is in the microwave frequency? So at microwave frequency, the frequency is quite higher, as we know that. I think the earlier class also I mentioned it. Yeah. Yeah. So in earlier class also I can use that, erase it, which is not necessary. Okay. So we'll take a pen. So here at microwave frequency, I think this color, if it is not very clear, I can change this to some other color. So if you take microwave frequency at for example, let us take frequency is 3 gigahertz. I think it should be, I think if it is legible, I'll see. So frequency is 3 gigahertz. What is the wavelength? So wavelength is nothing but c by f. So c is speed of the light. If I write in terms of centimeter, 3 into 10 to the power of 10 divided by the frequency is 3 into 10 to the power of 9. So if I solve this, I will get 10 centimeter. This is my wavelength. So if I start using at microwave frequency, it's 3 gigahertz is quite a beginning level of microwave. It can go till 300 gigahertz microwave frequency. So if I increase the frequency, the lambda is become very smaller and smaller. It become a millimeter. So in that case, the physical length of any network components, if you take a filters or if you take a transmission lines or amplifiers, the physical length what I can maximum I can design for example, I can design 1 centimeter amplifier, the physical length. So what happens if the physical length is comparable to the operating wavelength, though we started realizing the instantaneous change in the voltage and current, as we have seen in the transmission lines. When the frequency is higher enough, then wavelength become very shorter wavelength. So shorter wavelength when becomes this wavelength is going to comparable with the physical length of the network components. So the network components in the physically, it will start realizing the changes in the voltage and current with it itself. So within itself the change is going to happen, voltage and current. So we cannot exactly know exactly what is the voltage and current of that particular network. So if we take circuit theory, we need exactly, for example, if this is the 2 resistor R1 R2 connected together, there is another resistor connected to the parallel. So this is a T network. If I want to use the circuit theory, I should know exactly what is the voltage here. Let us take V1. What is this voltage? I think both are parallel. So let us take, this is a kind of V2, this is a V3. So the current is going to change. So I should know what exactly the voltage and current in each node to apply KCL and KVL. So that is not it's possible at higher frequency. So we have to find out the solution for that. So how to solve this network voltage and current circuit there, how to apply it for higher frequency, so that we need to find out. So here we will use that perhaps field analysis, or if you see that so perhaps field analysis or wave theory approach is used when circuit analysis is not feasible. So this one condition I told you, that at a higher frequency, if I don't know voltage and current exactly, I cannot apply the circuit theory directly. In certain extents that you can use the circuit theory. For example, if you take a TM lines, like exactly if you take a coaxial cable or twisted pair, still if there is a field going inside, even though physical length is comparable to the wavelength, if I can find out approximately the voltage and current in two edges of the conductor. So this is only applicable in TM lines, not in the network components. So if you take that transmission lines, TM lines especially, that is TM lines is transfer electric and magnetic. I just told in earlier class, this electric and magnetic field is perpendicular to the direction, that is we call as a planar wave. So TM lines especially need two conductors, that also mentioned earlier. So two conductor transmission line, what are the examples? You can say DTH cable, coaxial line, where you have an inner and outer conductor, and you have a twisted telephone lines that has the two conductors. So wherever the two conductor lines is called TM lines. So in the TM lines, even though it is a higher frequency is going, still I can write the equivalent voltage and current in each terminals or each end of the terminal. If I able to find out voltage and current, then I can apply the circuit theory. This is not applicable for a waveguides where it is a non-TEM lines. So waveguides is especially a single conductor, only TE or TM modes will propagate, and with respect to different mode numbers, so it is voltage, current is going to change, so it is really hard. I can apply the circuit theory. So this is crux or base of analyzing the microwave network. So this is what I told. If we able to find out voltage and current at higher frequency circuits or components, then I can write the equivalent and find out the impedance, then I can apply the circuit theory approach. So that's why I told we are not totally ignoring circuit theory and going to some other approach. Wherever is feasible, if I able to find out voltage and current in a equivalent voltage and current and impedance, then I can apply the circuit theory, obviously. So that what I told, in microwave frequency the voltage and current is difficult, but it is not impossible. In coaxial line I can even write equivalent voltage and current. That is a little, you can see it a theory or a proof in the textbook also. That is a derivations part you can see, but normally if TM lines I can write the equivalent voltage and current. So how to find out? Apply that field analysis concepts, electric field and magnetic field concepts, and write the equivalent of that electric field equivalent to the voltage, and magnetic field H, that is equivalent to the current. So using that I can write the voltage and current, and from that I can find out the impedance and also the voltage and current of what is flowing onto the transmission line. And clearly define terminal, that what I told this for a coaxial cable, microstrip lines or twisted pair. Microstrip line is a printed microstrip lines. Wherever if I have a two terminal pair, I can apply that equivalent voltage current concept, then I can find out, use the circuit theory. And but this is not strictly exist for non-TM lines. For example, rectangular and circular waveguides, I cannot apply this equivalent voltage and current I cannot find out easily, because it is not it is very complex. From field analysis concept to the circuit analysis for non-TM lines is quite complex. So we don't usually find voltage and current for non-TM lines. For waveguides, rectangular, circular waveguides, we don't find it equivalent voltage and current. Instead of that, we will use that another technique to find out the node voltage, node impedance, especially that we will use that some other technique. So for non-TM lines, circuit theory approaches of finding VI is complicated, since it depends on varying fields. Because non-TM lines, you have a field is varying in each on the space, because you can see that waveguides, the electromagnetic signal is traveling inside. We cannot instantaneously find out voltage and current.